Okay, so number 5 is actually very similar to a problem from today's notes. So hopefully between these two explanations, these types of problems will make sense. The lamppost problems are classic calc problems. So we have a 7-foot tall person walking away from a 20-foot lamppost. So basically here's our lamppost and we're going to make a triangle. And here's our person. And the lamppost, the light is making a shadow. Again, this is our, just make them kind of look like a person, okay? So this is the 20-foot tall lamppost, 7-foot tall person, not drawn to scale, obviously. And now what we have, so we're looking at the length of the person's shadow. This is the person's shadow because it would end up being like this, okay? Like that's where his shadow would show up. So that's the length of his shadow. I don't know what this is, but I'm going to call it this distance x, the distance from the person to the person is away from the lamppost. And then our equation, so there's our picture, and again, this is a right triangle. These are both right triangles. We're assuming, it's an upright lamppost, not leaning, and the person isn't leaning either. So now we can set up a proportion, and this is how you always do these lamppost problems. We have our large triangle, which is this one. And then we have our smaller triangle right here. Okay. So basically 20 over this whole distance, which is x plus s, equals 7 over s. Okay, so height to horizontal length equals height to horizontal length. And they're similar because basically all the angles will be the same, because I know this angle's in both, and they both have a right angle, so this angle up here will also have to be the same. But don't worry too much about that, just know that this is how you set up the problems, but that's why it works. So now if we cross multiply, we have 20 times s equals 7 times x plus s. So 20s equals 7x plus 7s. Subtract 7s. So now 13s equals 7x. So now we differentiate because that's the most simple form of our equation. So we have 13 ds dt equals 7 dx dt. Okay, so now let's look at what we know here. So a 7-foot tall person walking away. He's walking away from the lamppost at a rate of 5 feet per second. So then this distance here, he's walking away. The rate of change in x then is our 5 feet per second. So this is 5. So 7 times 5 equals 13 ds dt. So 13 times ds dt equals 35. So ds dt equals 35 over 13. So now what we're looking for is the rate of change of his shadow, and ds dt, I mean that's this length. That's how the rate at which that length is changing. So then at what rate is the length of the person's shadow changing when the person is 16 feet from the lamppost? Well, it turns out we don't care how far they are away because the person's walking away at a constant rate. So the length of the shadow will be also changing at a constant rate. So ds dt then is 35 over 13 feet per second, and that's the rate of change of the shadow. So now we have an observer standing 700 feet away from a launch pad to observe a rocket launch. The rocket blasts off and maintains a velocity of 900 feet per second. So if we think of a picture here, our picture, so we have basically a person is like right here, okay? He's watching the rocket launch. The distance from him to the launch pad is 700. So he's not moving, so the distance to the launch pad is always going to be 700. Then we're assuming it's blasting directly upwards, So it's a right triangle. Finish the right triangle. We're assuming that the distance the person to the rocket is measured along this diagonal. This requires a lot of assumptions. Honestly, I've always found anything sort of related to physics required a bunch of assumptions, so here we are. So we're looking at the distance from the observer to the rocket. Here's the rocket. I'm not even going to try to draw a rocket, but we know it's going upward. Okay. Distance from the observer to the rocket, this is going to be d. Let's say this is like h. Okay. So then we have a right triangle. So then 700 squared plus h squared equals d squared. So there's our equation. Okay, so now basically if we take the derivative, this goes to 0. So we end up with 2h dh dt equals 2d dd dt. That sounds like kind of crazy, like you're singing some sort of goofy dt song. Maybe I'm just crazy. So we have 2h dh dt equals 2d dd dt. And now we're looking at, okay, what can we fill in? The 700 we really already used. The velocity is 900 feet per second, so that's the change in the height. So this is 900. 2h is actually 2400, okay? Because the height from the ground, 2400 feet from the ground. I'm going to write this a little more spread out. So we know we have our 2, our height's going to be 2400, our dh dt is 900 equals 2d dd dt. Well, we have two variables. We're being asked how fast is the observer to rocket distance changing. So what we're trying to find is dd dt, so that means we'll have to be able to figure out d. Well, we can. We have a right triangle. So if h is 2400, we can set up 700 squared plus 2400 squared equals d squared. Let's see, 700 squared plus 24 squared. That's 6,250,000. Take the square root of both sides. Our distance is the square root of that, which is 2,500. You can rewrite one more time. 2 times 2,400 times 900 equals 2 times 2,500 times dd dt. So 2 times 2,400, and you can solve this all at once if you want, but so this left side is 4,320,000. And this is 5,000 dd dt. So if we divide by 5,000 on both sides, we end up with dd dt equaling 864, and then you look at our units, feet per second. So that's how fast this distance right here is changing when the rocket's 24 feet away from the ground.